is B prime if and only if B is same as EI tilde B prime. And I'm afraid this blackboard becomes more and more like undergraduate students' answer sheets of the examination. Go back to the next page. I solved number 6 first, something like that. Okay. But anyway, here, the point is that, yes?
And you have error.
And?
So PQ lambda is a CQ vector space,
Yes.
right? And then you have A0 is smaller than CQ.
Yes.
Right? So you have something. And you are considering tensor that with A0 and C and electrical C basis.
Right.
So what is the dimension? I mean, which one is bigger? B as a C vector space, or VQ lambda as a B as a basis space?
Great. That's the point. So here, let us first observe the following. Well, since EI tilde and FI tilde can be regarded as or considered as inverse to each other, almost inverse to each other, we can define a graph structure, say B I arrow to B prime, if Fi tilde B is B prime. So the set B with this graph structure is called the crystal graph of VQ lambda. Okay? So we can say B the crystal or crystal graph of VQ lambda. Then what's so important about B? As Professor Saw mentioned, actually the number of elements in B is the same as dimension of L of QL, which is the same as the rank of A naught lattice L. But since A naught lattice is a free A naught lattice of VQ lambda, that must be the same as dimension of VQ lambda over CQ. Okay. So the crystal B contains most of combinatorial informations of irreducible high-state module VQ lambda. Okay. So to understand the structure of VQ lambda, in many cases it suffices to understand the structure of B. Okay. So in this case, B is denoted by B lambda. Okay. The crystal or crystal graph of the irreducible high-state module VQ lambda. So our goal is to find a combinatorial realization of B lambda. Okay. And for this purpose, let me tell you about one very interesting and important property of crystal basis. Suppose B Vj is the crystal. I will omit crystal graph. Crystal of Vj. Here J is 1 and 2. So consider two UQG modules and their crystal graphs. Okay. And then we can ask questions. First, what is the crystal for direct sum? Okay. So what is the basis for direct sum? It's just a union. Okay. So this will be just a disjoint union of two graphs. You put two graphs side by side or whatever. That's the answer. But what is the crystal for the tensor product? Okay. I remember I had difficulty in understanding the tensor product of vector spaces or R modules in general in undergraduate days. And I think it is defined in terms of diagrams and universal properties. And,
Very bad.
and I wish I could teach tensor product to be the vector space whose basis is, well, I mean, what is direct sum of vector spaces? It's a vector space whose basis is the disjoint union of two bases. And what is tensor product? It's a vector space whose basis is the same as the Cartesian product of two bases. So that's, well, then from the definition you may be able to deduce all bilinear properties and universal properties, I think. Anyway, so that's the tensor product. Therefore, the crystal for this tensor product is naturally, as a set, B1 cross B2. Okay, what is crystal for? So B1 cross B2 as a set is a crystal for V1 tensor V2. But this is not a graph. The set of vertices is the set of the Cartesian product of two sets. How to define graph structure? For that purpose, let me introduce the following. So suppose we have an element in B, and then suppose we have I arrows passing through B. So here are the I arrows. The number of I arrows coming into B is denoted by epsilon IB. This epsilon I is different from that linear functional epsilon I. Okay. Sorry, but this is phi epsilon I. This is phi denoted by phi IB. Okay. We can say the number of arrows coming to B and number of arrows coming out of B. Okay. And then, how do we define the arrow structure on B1 cross B2? So we may define Fi tilde only, because Ei tilde can be defined to be the inverse of Fi tilde as a graph. And B1, B2 is the following. First, we act on the first component. If phi I B1 is bigger than epsilon I B2. Okay. And we apply Fi tilde B2 if phi I B1 is less than or equal to epsilon I B2. Okay. But, so here, B1 cross B2 with the graph structure will be denoted by B1 tensor B2. And then so I will use B1 tensor B2 for the elements in B1 tensor B2. So we may replace these things as B1 tensor B2. And what it says is that, well, if this condition is satisfied, we draw the graph, or we draw an arrow for the first component. In the second case, we draw an arrow in the second component. And let us look at this through pictures. For example, so if we have B1, Kashara writes this way. So here is B1. I will drop the notation I, because we will consider only one arrow, and one color arrow. Here is B2. Okay, say this one. I mean, usually, I think when you make multiplication table over any finite group, then you would consider B1 times B2.
But even at one point,
Yeah.
FIs are all,
You are going to,
to one point. Is there any 2 points coming to 1 point, or it is impossible?
you mean if we consider, say, I arrow and J arrow,
Yeah, I mean this arrow, yeah, so
you mean from one point, can we have both I arrows?
or coming to two elements coming to 1 point.
That's not possible, at least in this case.
This is not possible?
It's not possible, but if I and J are different, then it's possible.
Yeah. What is I? And then this I's are the number of sequences.
You fix I, then you have a string of I's, I arrows. Then for that string only, you count the number of I arrows coming into B and number of I arrows coming out of B.
Okay. If you have different J's, then you have another.
You have another string.
Many. So at least I n minus 1 strings, right?
That's right.
Yeah.
Right.
That's what
For many other different arrows, right? Colored arrows. But in this case, suppose you have just only one arrow.
because this FI is the action, or?
Fi tilde is the action, yes.
So that's
Yes.
why you have
Right.
one string.
Right. And
But then you have a loop. Is it possible? No, if you-
in general, it's possible for general Casimir algebras, but for high-weight modules, it's not possible because by applying Fi tilde, then you subtract alpha I from the weight, so you cannot go back to highest weight. At least for finite dimensional modules. Okay. So here, let us understand what the tensor product rule means. I put too many dots, I think. Okay. So consider here, what is this? This is B1 times B2. Right? What is phi B1? Phi B1 is this, 2. epsilon, 틀린 거 아니야? epsilon B2 is 2. Then that's the second case, right? That means the arrow acts on the second component. So first component means go to right. Second component means go down. Right? So in this case, we need to go down. Right? How about here? And phi is the same, but epsilon is smaller. So should go to right. Right? And you may notice that this line is the line where phi I B1 is same as epsilon I B2. So if it's positive direction, then go to right. Negative direction, then go down. So what it tells us is this. Okay. And those who are familiar with SL2 theory, Lie algebra SL2, then this actually tells us is the so-called Clebsch-Gordan decomposition formula. And this is what? 1, 2, 3, 4, 5. So highest weight is 4, highest weight is 3. So 4 times 3 is, like a physicist say 4 times 3 is what? 7 plus 5 plus 3 plus 1, right? 7 means 8 dimension, 5 means 6 dimension, 3 means 4 dimension, and 1 means 2 dimension. So that's how we decompose tensor product of crystals. Now, what we will do is to realize the crystal graph B lambda in terms of Young diagrams. But here is basic example. So, example, take lambda to be epsilon 1. Okay. Then consider n-dimensional vector space V sub n. Then let Kj acts on Vi to be what? Q to the epsilon 1 Kj Vi. So what it means is actually Kj, this is always same as what? Q times Vi if J is I. I think. And Vi otherwise. Vj, Vi otherwise. What is this? I don't understand. J is I, yes. No, I'm sorry. 1. And J is 1, right? I think it is. I'm sorry. I was completely at the loss. This should be epsilon I. I consider the weight of each Vi is epsilon I. So it should be epsilon. So what I wrote first is correct. But this was wrong. So I, then what? When J is not I, what? Does it make sense? Yeah. Okay. And EI acts on Vj, V EI. Okay. Vi if J is I plus 1 and 0 otherwise. And Fi acts on Vj to be Vi plus 1 if J is I and 0 otherwise. Okay. And then V becomes UQGLN module. I'm sorry, I made another mistake here. Q to the Kj. Okay. 지혜 뭐하니? 이런 거 다 지적해줘야지. 선생 틀린데 가만히 있어. 빤히 보면서. 내가 나 망신당하길 원하는 게야. Okay, then what? So from here, we can see that we have the following graph. Actually, there is no, well, the string decomposition is unique. Only length is 1 or 2, depending on people. If you act twice, then you will get 0. If you look at the action, if you act, say, fi twice, then you will get always 0. So this is the graph. And we will denote by boldface B the graph from 1 to n minus 1 to n. Okay, 1, 2, n minus 2, n minus 1.
What is this 1 to n minus 1?
So it means if you apply f1 till the v1, then you will get v2. And then f2 till the v2 is v3. Yes. And recall that by I arrow, we mean the image of B under fi tilde is B prime. Okay. So this is the basic example of crystal graph for the so-called this natural representation or vector representation of GRN.
What is lambda? Lambda is just what does that?
Okay. This is the highest weight. So the weight of 1 or V1 is epsilon 1. And by F1, you subtract alpha 1, which is epsilon 1 minus epsilon 2. Then the weight for 2 is epsilon 2. If you subtract alpha 2 again, then weight here is epsilon 3. So at each time, weight will be epsilon j's. Okay. I think I'd better stop here today. And I prepared 4 lectures actually, but I'm finished with the 2 lectures. So maybe tomorrow I can finish the 3rd part, and if time permitting, which is quite doubtful, but anyway. So from tomorrow, at least we can play some games with combinatorics. We will deal with tableau, Young diagram and Young tableau, skew diagram, skew tableau, and some graphs. Okay? So thank you very much.